There's another function notation that is used a lot in upper division mathematics, but very rarely in calculus or lower division mathematics. And that's like this. So in differential calculus, in integral calculus, right? You know, we deal with functions of this type. We deal with functions of this type. Functions that map a real number to a real number, right? In other words, y equals f of x. F is a function of a single variable, right? Y is a single variable, right? But in here, this is where, in this class, we're going to start getting you warmed up to some deeper ideas that you'll see in 224, I think it is. I haven't taught that class here yet, so I don't know the number. The multivariable calculus. But what's going to happen, what we're doing in this section, is we're looking at a function. So this is like maps R into R2. The domain is one-dimensional. The codomain is two-dimensional.
Oh, remember that.
Also known as, this is called, sometimes this is referred to as a vector value function. The input's not a vector, but the output is a vector. You see?
Ooh.
So, and then, you know, so that's kind of what we're doing in here, right? In our sequences, series, we've been doing a lot of sequences and series, but we're about to change gears, you know. And we're getting into some more like vector analysis. That's what I would call it, at least. And when you get into multivariable calculus, you'll be looking at functions of where the domain is two-dimensional and the range is one-dimensional. You're even going to get even crazier and look at functions of where the domain is three-dimensional and the codomain is one-dimensional. But thankfully, it won't get much more complicated than that. If you were to take complex analysis, which is not even offered at a junior college level, right? Then you can look at a function of where the input's a vector and the output's a vector, vector to vector. That's weird stuff. Even that's pretty weird, but we're going to keep things simple, if I can say such a thing. In fact, in this class, we will, I think, I haven't checked the homework exercise to see if we're going to do this, but it will be within our range of capabilities to even do something like go from R into R3, right? These are both examples of vector value functions. This would be a vector in the plane. This would be a vector in 3 space. And that's a part of what we'll be doing in vector analysis. Is we're going to start getting more, we want to get you to start feeling comfortable with dealing with 3 space. We're not going to be restricted to the plane anymore. And yeah, so when you first got exposed to parametric equations, right? You know, we were actually looking at something like this, right? We've already worked with functions like that, although we didn't make it very explicit that this was a vector. We looked at, like, just so on the, for example, I could just make up something, you know, like so you see, x, I'm treating x not as a variable, but as a function. X is a function of t. Y is a function of t. Get it? And it's a function of t in the familiar sense. For x, the input is a real number, the output is a real number. Right? So x as a function maps a real number to a real number. Y as a function maps a real number to a real number. Those are the ones we're comfortable with. But f, as an input, you're plugging in a real number, but as an output, you're coming out with a vector. So for example,
Okay, so that like superscript 2, that's just like, that's just saying like,
that's just the dimension.
okay.
Yeah. So actually R2, this is kind of like getting into set theory now, but R2 is just shorthand for R cross R. Now this is not multiplication as you know it. This is called the Cartesian cross product. So when and I can tell it's not multiplication as you know it because that's not a number, that's a set. R is a set of all real numbers. Cross with a set of all real numbers. This is literally, by definition, means it's the set of all ordered pairs where x and y are real numbers. So if you see, if I write R3, what I really mean is a set of all ordered triples where each of the coordinates are real numbers.
Okay, but we're gonna start with the 2.
Yeah.
Alright.
I think that there was like easy way, like just list all like number and then like close.
I don't know, maybe.
Matrix.
Oh, you're thinking of matrices?
Yeah, you're talking about like
But
with
like
A,
actual ones.
A1 times A2 plus B1 times
Could
B2.
be.
What was it? Actual ones rule?
Yeah, reduce row echelon. Yeah, that's matrices. Yeah, that's a little different from this.
Oh.
Yeah, but that's a thing. Yeah. But yeah, so like for example, I can make up some functions, and this isn't prepared. I'm just making up 2 functions of t, such as t squared and sine t, maybe. Right? And based on this function, I can evaluate this function in a very simple way. That's kind of what you've already done in 7.1, right? For example, you can plug in 0, and you get a vector. What vector do you get?
0, 0.
Oh, okay. That's kind of a trivial vector. It has no length at all. It's the only directionless vector. That's kind of boring. What if I plug in 1?
That's boring.
1 0 point something.
Yeah. The sine of 1, that's 1 radian, right? Somewhere in the first quadrant, so I guess this is somewhere between 0 and 1. So if I was to evaluate f of 2 then, right? I don't know, let's see, let me think, 0.5. 1 radian is like almost 60 degrees. So I'd say it's approximately, I think it's a little less than 60 degrees. So since the sine of 60 degrees is root 3 over 2, I don't know, whatever, good enough. Root 3 is about 1.7, half that 0.8 is 0.7. Roughly speaking, you can, if your calculator is in radians, you should get something in that ballpark, plus or minus 0.2. Really rough.
Is it supposed to be like smaller than sine 30?
0.8. Okay, so it's closer to 0.8.
Oh.
Yeah, sine is the y coordinate on the unit circle. Cosine is the x coordinate. Whereas 2 is somewhere in the second quadrant. anyway, that's going to be about 4. Actually, it's probably going to be about that, actually. Yeah, maybe it'd be better if I had plugged in like, something like pi over 2. But then now it's going to be harder to see what the x-coordinate is. You know what I mean? But at least I know that the sine of pi over 2 is 1. Right? So if you actually if you were actually trying to graph this, you probably would need to like kind of, I need to get a calculator to estimate this so that I know where to graph it. I need to know what pi over 2 really is. 3.14, 1.57, is that right? So this is like f of 1.57 is approximately whatever that is. I don't know, 2.3. You know what I mean? So I can see that and we refer to this as the parameter. If the parameter is 0, it maps to this point. So I'm not actually graphing. Notice this is x, this is y. There is no t-axis. I am not representing t on here at all.
Why not?
There's no room for it. And we just kind of like, yeah, I just know that this point corresponds to when this is when t equals 0, right? But when I get up to 1, when t equals 1, I get to this point, which is at 1, comma 0.8, maybe about right there. This is when t equals 1. If I want now, I moved somehow from here to here. If I had plugged in 1/2, I probably would get some point around here. I'm not really sure whether it's curving up or curving down, or maybe it's just kind of going up here and then coming back to there. Who knows? But if you want to answer that question, you just plug in like 0.2, 0.4, 0.6, 0.8, and just sort of connect the dots, right? Before I get to 2, maybe I should pass through this one. Pi over 2 is somewhere between 1 and 2. In that case, I would get 2.3 and 1 or so. This is when t equals 2. I mean, sorry, 1.57. Right? But when I get up to when t equals 2, I get something more like over here at 4 and 1.8, we'll say.
So the parameter gives us a vector value, right?
Yeah.
But when you graph it, you don't draw them as a vector.
So the vector is basically describing a curve. So in this case, I get this vector. When t equals 1.57, I get this vector. When t equals 2, I get this vector. But if I look at the set of all the heads of these vectors, it traces out a curve. See that? And we can kind of talk about the shape of that curve. What does that curve look like? And I'm kind of assuming that it kind of follows this sort of. I'm not 100% confident that's what it looks like, but I'm just kind of guessing just based on the points that I have. Probably looks something like that. And from what I've discussed up until this point, minus the fancy notation, this is what we did at the very end of trigonometry. So that 7.1 was technically a review, but probably a needed review.
And you're saying the head of the vectors from the origin.
Yeah. So whenever you have a function of a single variable mapping into a higher order space, it's sometimes referred to as a curve. So the vector value function, also known as a curve function, right? Or parametric function. But I think the describing it as a curve is the most descriptive. It's a curve in space, right? And notice that this curve doesn't need to pass the vertical line test. Notice that y isn't necessarily a function of x, right? X and y are both functions of t, right? So this So as you continue from there, this function could very well do something like this. And there's no problem with that. But yeah, but the question, what we want to do in 7.2 that you couldn't do in trigonometry is to pick a point, say this one right here, when t equals 1, and find the slope of the tangent line. Or even better yet, the equation of the tangent line.
The equation of the tangent line?
Yeah. But the equation of the tangent line, once I know the slope, it's no problem. Right? Because I already know the coordinates of this point. The coordinates of the point are right there. Or this is the exact coordinates right here. So if all I need is a slope, and if I know the slope, I can write the equation of the tangent line. Right?
And that slope would be the same as taking the derivative of each like of t squared and then sine t, plugging in this value.
Say again? Oh, right. The derivative would be the same as what?
Like, so like when you have a function, you take a derivative. So like to get the derivative of that parameter, you just take the derivative of t.
Yeah,
X and y, right?
Yeah, that's a good point. So like to take the derivative of this, right? You'd want to be very cautious now because this is a different kind of a creature that we haven't really dealt with a function like this before, right?
Yeah.
But I think if I'm hearing you right, you're saying that the derivatives should have something to do with
Yeah. No, I'm just asking
this
because
and
not.
that, and your intuition would be correct, right? But yeah, but I certainly would be cautious because this is a kind of a different kind of a thing, you know. We know that we know from differential calculus that if you have a function where y equals f of x, you would have taken the limit as h goes to 0 for f of x plus h minus f of x all over h. No problem, right? That's with the normal function of a single variable to a single variable. So how much does it change when what I'm mapping to is a vector? So the bar is just a vector, right? Well, it turns out it's not much at all. If I go ahead and I'll go ahead and use this as my definition for f, and I'll change this x into a t just so that it's not because x actually means something here. So I'll change this to a t plus h and a t, right? And according to that, it would be the difference between two vectors. Can you subtract vectors?
Yeah.
Yeah, that's something also that we did at the tail end of trigonometry. In this case, the vectors are, oops, my bad. The input's t plus h, not t. Not much room. T plus h and t plus h.
So at that point, the h will be the distance between the two vectors.
It's the distance between the two parameters. So here the parameter is t. Here the parameter is t plus h. Now when you plug it into these functions, depending on what the functions are, these two could be very far apart from each other. They could be really close to each other. Who knows? But geometrically, you might recall that when you're subtracting two vectors, it's kind of like finding the distance between the two heads of the vector. And computationally, another thing we discussed is that, if you subtract two vectors, it's actually not that bad. You just subtract the x-coordinates and subtract the y-coordinates and you're done, right? So the numerator would become that. And since division by 1 over h is the same thing as multiplication by 1 over h, and 1 over h is technically a scalar, so I can distribute the scalar. So So this is the same thing as a limit as h goes to 0 of each coordinate divided by h. Now, by the way, the details I'm going through right here is more of like a theoretical exercise. So you're not going to have to be responsible for the theory, just the result that I'm attempting to prove. And along with it, it might be more memorable if you understand why it works. Right? Now, this is a vector that depends on h. And as h gets close to 0, the limit of a vector is the same thing as a vector of limits. In other words, this is the same thing as
Man, he came to class on the right day, bro. Carter was just out of luck. He's gonna ask me. He's like, no, I have no idea what we're talking about today.
well,
We have YouTube, so.
Yeah.
the good news is x and y are functions in the familiar sense. That means that this coordinate is what it was back in differential calculus in 151. So this is, by definition, that. And the second coordinate is that. Right? Which means that finding derivatives of these vector valued functions is actually pretty easy. All you need to know is what's the derivative of t squared.
2.
And the derivative of sine? I could have made this a lot quicker. I could have just said, in the church of mathematics, we don't ask why, it's just, it is what it is. The derivative, you just take the derivative. You know? But in fact, you know, we can see it, you can get a little glimpse into why, you know. That's what's happening under the hood, right? And that gets us to here, right? This is the derivative of the vector valuing function, but what does it mean? What does that give me?
Tangent vector.
What it gives you, yeah, it is kind of a tangent vector. Let's see what happens if I plug in like 1, for example. What do I get? If I plugged in 1, I would get 2 and cosine of 1, and that's approximately 2 comma. Well, cosine of 1.
So like
0.5. Makes sense. Because 1 radian is pretty close to pi over 3. Right? So 0.5 over 2 up 1/2. Right? The vector you get, I wish I had a third color.
Yeah, I'm confused because that doesn't.
Yeah, the vector you get is kind of like right here. It appears to be like right on top of that one. That's just a coincidence. But this vector right here actually is a tangent vector. One thing we said is that, well, one thing I said before back in trigonometry is that a vector is determined by the magnitude and direction, but it's independent of the position. So I can, as long as I keep the same magnitude and direction, I have the freedom to put it wherever I want. And if you put it right here, it's going to be a perfect tangent vector. Right? So this is my tangent vector. And that's what this gives me. And then, but it's a function of t. And furthermore, but if I want to write this, the equation of this line, right? Well, there's two ways to do it, right? We can do it with rectangular coordinates, or we can write the equation of this line with parametric equations, right? In this class, you're gonna need to know how to do it both ways. Okay. So it turns out that with parametric equations, it's actually a little bit easier than it is to do with rectangular coordinates. But because rectangular coordinates is probably more familiar to you, we'll start with that. Right? If I know,
We could just write it like r theta.
yeah,
We just write it that way.
yeah. Well, like that, r theta, that's kind of like this. I'm using f instead of r. More standard would be to use r, usually for space curves. So yeah, so I think probably after today I'm going to start using that convention. But that's just, just the letter that's popularly used. And oftentimes it'll be convenient to let the parameter be an angle. And especially if it's if it's following the shape of a circle. You know what I mean? So yeah, so sometimes the parameter will typically be t or theta, right? And yeah. But yeah, like, okay, I see what this vector is, but what is the slope of that line now? What's the slope of that line? How is this, from this vector, can I extract the slope?
Yeah, if you know the values, yeah. Just use arctangent, right?
Yeah. I know that the coordinates of this vector are here. And what were we saying?
You just use arctangent to find the slope, right?
Well, arctangent would give you the angle.
Oh, well.
Yeah. Arctangent would give you this angle right here.
So
it might be helpful to think, okay, well,
just, yeah. Cosine, yeah, sine, the sine of that, cosine of that.
if this is 2, and this is the cosine of 1, you think of it just in terms of rise over run.
Yeah.
The slope then would be cosine of 1 over 2. Right? So yeah, so once you find the derivative, as a rule, you could just basically take the y-coordinate divided by the x-coordinate. That would be the slope. Right? It's as simple as that. But yeah, but what just happened is we've just invoked the chain rule without realizing it. Why is this the slope? Is because of the chain rule.
What?
We're reviewing all kinds of weird things, right? Remember what the chain rule says? If you have a function within a function, you take and you want to know the derivative of it. You gotta
Leave it alone and then take it inside.
So yeah. So in other words,
So how did that just happen?
well, okay. If suppose, so let me give you an example of a function within a function. Suppose like b is f of a, and c is g of b. Right? Then c is g of f of a. That's a composition function. So if I want to know the derivative of c with respect to a,
G prime f of a times f prime of a.
g prime and f of a, keeping the inside the same.
Yeah, times the f prime of a.
Yeah, that's the chain rule. But Leibniz notation is actually much more enlightening, actually. I wanted to write it this way so I can invoke Leibniz notation. Another way of saying the same thing, because g is given by, notice f of a is b. So dc dA is the derivative of c with respect to b. Because this is b.
Right.
The prime is kind of vague. I don't like the prime notation because, especially when you have like functions of different variables floating around, it's like, okay, is that the derivative with respect to a or the derivative with respect to b? This notation is much more clear on that point. Multiplied by f is b, basically. It's the derivative of b with respect to a. It's just saying the same thing with Leibniz notation, right? And what this is saying, as another way of stating a chain rule, that's the chain rule, right? For our viewers at home, I'll label this. That also means that the derivative of c with respect to b could be computed as the derivative of c with respect to a divided by the derivative of b with respect to a. And that's what we're using in this class, where a is the parameter. You see what we did here? So when I have a function right here, a vector-valued function, and I take the derivative of it, well, let's see here. Instead of writing x prime of t, I'm going to write it like this.
dx dt.
Yeah. So when I take this coordinate and divide it by that coordinate, I'm taking dy dt divided by dx dt, right? The chain rule says whenever you're taking the derivative of two functions with respect to the same variable and you divide them, it ends up being just dc with respect to b. So this equals dy
dx.
dx. So notice that dy dt is not the slope of the tangent line. Dy dx is the slope of the tangent line. So the chain will be useful if you're trying to write this in rectangular coordinates, right? So now I can see in this case that because the coordinates of this point is given by the vector, right? We said it was when we plugged in 1, we got 1 and sine 1. Right? Over there's a vector. If I put it in parentheses just to emphasize it as a point, I'm treating it like a point here. And so that means that the equation of the tangent line is given by y minus sine 1 equaling the slope times x minus 1. Yeah, 1.
But since the vector is like, and you said like, they don't matter about position,
Mm-hmm.
can we just like say they're all go to the origin? You know what I mean?
But I'm not using the vector. I'm using the slope.
Okay. Try.
And that's the type of equation that we've worked with, for some time now. Right? But yeah, we're gonna want to get good at expressing these tangent lines in terms of a parameter as well. It turns out if you do it with a parameter, it's actually, I think, easier, even easier than that, right? I would say.
Just curious, differential equation, is there like differential equation course or
With differential equations,
like,
what about them?
is there any, is there a class like in pure college or like calculus? I think
Yeah, it's
some
before
yeah, they have.
the integral one.
Mm-hmm. Yeah. Yeah.
So you're too smart. You already started after that.
No, I mean.
Yeah, 151. That's the class.
Differential equation.
Oh no, equation no, it's different.
Yeah.
Yeah.
Differential equations. Yeah.
I-
At the end of integral calculus, we dabbled a little bit with some differential equations.
Yeah, they got that 234, or 205. It's one of those.
200 something.
Yeah.
Okay.
They have that.
Yeah, because I heard like some college they don't have like the name. They have like something like calculus 4 or something like that. I don't know.
Yeah.
But I feel like those are in differential equation as well.
Yeah. In differential equations, it technically, as stated, it's not a differential equation. But yeah, you're gonna a lot of times we have differential equations where, like the ones we looked at before, they were very basic, primitive differential equations where the solution was a normal function, a familiar function from a single variable to a single variable. But there's also differential equations where the solution could be a vector value function. You know, just, in fact, yeah, if you're modeling like, a trajectory as it passes through the air, these techniques are actually much more useful than what you do in entry level elementary like physics.
Oh yeah, I think I've seen it for like when you have like the like satellites like escape like force
Oh yeah,
and it like
Mhm.
like
Sure.
moving.
Whenever you have all these different forces interacting with each other, you're going to use vectors. Vectors is going to make it a lot. It will still be hard, but it makes it a lot easier than it would have been otherwise. Yeah. So yeah, so you'll need to know that, and I think that's really the only thing that's new in 7.2 is that kind of stuff. Not much else. Oh, actually no, there is else.
There is those.
Yeah. That's right. That's why I have notes. Let me look at my notes. Oops, wrong class.
That was rough.
But I mean, if we trim out all the theoretical stuff, in summary, I've said that the derivative is just take the derivative of each part. If I was mapping into 3 space, it would be a natural extension. I just have x as a function of t, y as a function of e, and z as a function of t. I just take the derivative of that too. You know what I mean? If I am in 2 space, then the slope can be computed using the chain rule right here. And that's pretty much it. That's all that I've really said. That's how you do it.
So in like three-dimensional vector, so you do it's pretty same, but like it will be like dz over dt over dy over dt over dx.
Well, see, the thing is, in 3 space, what do you mean by slope?
It's like
In 3 space, you're going to have an x-axis, but instead of drawing the x-axis going sideways, it's going to be coming straight out at you.
right.
The y-axis is going to be going out to your right, and the z-axis will be coming straight up like this.
So it's like the slope between x and y. I mean between a and between x and y. No, between I'm sorry, between x and y and
Sure.
z. Does that make sense?
Well, the thing is that, okay, as you go this way and this way, this is x, this is y, and this is z.
Right.
If I pick 2 points,
Right.
there's a natural sense of slope, right? And I think that's what you're describing.
Yeah, right. So x, y, and then just 2 of this.
Yeah.
It will be like in middle of x and y, and then just lift it up to not lift it up like this.
Well, what you're describing is what's called a directional derivative. A
Okay.
directional derivative. And that would have slope in the sense that we're familiar with, right? But slope as an idea unto itself doesn't translate well into higher dimensions.
Well, why not? Wouldn't it just be still the change in
in
change in this axis over the change in this axis?
in higher dimensions, you have a function of 2 variables, and the graph of it, we haven't talked about too much about this yet, but imagine like this undulating surface, right? The graph is going to be like this undulating surface. You know what I mean?
Oh, I see.
And
Yeah, I've seen that too.
And maybe this is part of the surface right here and has this kind of a bulge to it, you know. If I pick this point, it's kind of at this on the side of this hill, right on the surface. Like, what do I mean by the slope of the tangent line right here. It's kind of difficult because
Right.
it's not clear which line I'm talking about. Like this line might be really steep, but this line, which is also tangent to it, might have a slope of 0. If I have if there's a sense of, if there's an orientation to like which way is the positive direction, which way is the negative direction, going like this, maybe the slope is actually negative.
So it will be pretty much like the slope itself. It will be like plane. Plane. Like
Right. So
like this.
exactly. So what we do instead of talking about a tangent line, in 3 space we talk of a tangent plane. But what do we mean by the slope of a plane?
With respect to where the x, y, z is.
Yeah. So for a specific point, if I specify a point, then that determines if I a specific point on a specific surface, then I can speak of a tangent plane. But like, what is that? Like, what? We don't use the word slope in this case. We describe the incline of it with a normal vector. Every plane has a normal vector.
Okay.
So if the vector is going this way,
Yeah.
see that?
Right.
So I can speak with this vector. I can speak of if I know a normal vector. So kind of like, if I know the slope and if I know a point on the line, I can write the equation of the line. When it comes to planes, if I know a point on the plane and I know a normal vector to the plane, I can write the equation of the plane.
So really the normal lines or whatever is not really because we care about the normal line, but that's how you express the direction of the plane.
Mhm.
Okay.
So we're if we were to use the techniques of multivariable calculus back in like differential calculus, I would be looking at the normal vector to the curve. And from the normal vector, I could write the equation of the tangent line. But I wouldn't be using this formula for it, right? Yeah.
This is kind of like weird. I mean, not weird, but last time when I mean, it's a little while ago, but I didn't understand, right? But now I understand. I remember like the plane like x plus y plus z is equal to like d, right? Something like that. I didn't understand like what it is.
Yeah.
But it makes sense now.
Yeah, a lot of these things is you need to have time to really get good at it. You need some time to like struggle with it, and then put it down, and then come back to it, and then you start making connections that you didn't make before. You might have understood it well enough to at least get the right answer, hopefully. But when you come back to it, you start making some connections that you did, even though you're able to get the right answer, you start making other connections,
Right.
that sort of thing.
Yeah, connection. Yeah, I love it. Yeah, and because I think just solving the problem is not just that. I mean, it's a little different. I mean, you might understand, but I can still get the answer. But
Yeah. Well, let's see here. I'm gonna. I made up this example, but I'm gonna do another example that's pretty similar to this one, and I'm gonna use the one from the book so that I don't run the risk of it getting out of hand. So the nice thing about the book is I know it'll stay well behaved. These can get unruly really quick. So this is example 7.6. X of t is t squared minus 3.
X of t,
X as a function of t is t squared minus 3. Y as a function of t can be written as 2t minus 1.
2t minus 1.
Very often with parametric equations, they're going to specify the values of the parameter, like they do here. They say that t goes from -3 to 4. That makes sense? So they're writing the parametric equations the way we would have back in trigonometry, Taylor trigonometry, just as two distinct equations. And so I might be getting a little bit ahead of the book right here by just writing it like this. This is just two different ways of saying the same thing. Two different ways of saying precisely the same thing. I'm calling this curve, calling the curve R. And I'm showing that the formula for the x-coordinate is given here, formula for the y-coordinate is given there. And I'm only plugging in values of t that are in this range. So I can plug in -3 to see where the curve begins. I could plug in 4 to see where the curve ends. So this curve, has a definite starting point and an ending point. We've seen that we can compute, right, the derivative. Oops. Is that right? Right there. And from that, I can see that I can find that if you give me any value of t, I can compute the tangent slope there, dy dx. It would be this divided by whatever that is, right? So in general, I can see that dy dx is so the tangent slope could be expressed in terms of the parameter as well.
Wait, so the tangent slope could be
Expressed in terms of the parameter as well.
okay.
Yeah. So for example, if t equals 0, right, that's a point on the curve. Right, it's in somewhere between -3 and 4. I could plug in 0 and see where that point is on the plane. And I could plug in 0 here and see the equation of the tangent line. Well, that's an interesting one. It would be a vertical line.
Yeah, 0 t.
So the range will be changing, right?
Mm-hmm.
I mean, because -3 to 4 is like t is like domain.
Mm-hmm.
So for the function, it would be like 6 through.
Well, remember, there's no t-axis in there, right? There's only an x-axis and a y-axis. So it's tricky to kind of graph because,
Right.
Yeah.
you got to see what x and y are simultaneously as t increases.
So then the domain will be remain the same.
Yeah. So the domain for this function is literally a subset of the t. The domain is a set of t values. It's not a set of x values. The domain is a set of t values. So this is the domain right here.
Yeah, it's kind of confused.
Yeah.
It's there.
Yeah. But what the example in the book, if you're reading the example in the book, it's not asking us to find dy dx. It's asking us to find the second derivative of y with respect to x.
What?
I think.
With respect to x and with respect to t.
Well, maybe I read it wrong. No, it's with respect to x. Calculate second derivative. It says to calculate.
Which one is it?
Second derivative.
So wouldn't that just be the derivative of the slope? Or like dy dx is like,
So like this.
yeah, wouldn't it?
So it would be
Oh. Yeah.
It would, based on this, it would be
okay.
the derivative, the second derivative of y with respect to x would be the derivative with respect to x of dy dx. But as stated, dy dx is a function of t. So what I'm writing is true. This is a true statement. But x and t are interrelated. what is the derivative of 1 over t with respect to x?
0. No?
It would be 0 if t was a constant with respect to x.
But, oh,
What?
So this respected by x 1 over t. Isn't it like considered like constant?
This is only considered a constant if t doesn't change as x changes. If they're
Oh,
independent of one another, then it would be a constant with respect to x. But this tells me that x and t are interrelated. You see? At this point, to finish this problem, I'm kind of at a fork in the road. I can do a couple of different things,
Oh,
right? Probably the most primitive and basic, simple-minded thing to do, right, would be to think, okay, well, I can see that it's not 0 because x and t depend on each other, right? So x is equal to t squared minus 3. So probably I think the most simple-minded, straightforward thing to do is just solve for t. And substitute in there so it is a function of x, so I can see what x is, right? And since, now this is the tricky part, at this point I want to take the square root of both sides. You know what I mean? And that's tricky because in the domain, t could be positive, then again it could be negative. It really just depends on which value of t I'm talking about. Does that make sense? So I'm not even sure how to simplify this. I could put absolute value of t, but I'm kind of stuck right there. So I think the answer to this question is going to depend on whether t is positive or negative. You know what I mean? So let's just say, and again, that's doing it the boneheaded way, right? Simple, straightforward. But if I follow this path, I get stuck right here, you know? The absolute value of t is the square root of x plus 3. In other words, if I would expand this a little, I'd say t is the square root of x plus 3 if I know that t is greater than 0. But if t is less than 0, the absolute value is going to become a negative t. So I'd be using this formula instead. Almost looks the same, but it is a different formula. Right? Yeah. But, we push it through, and you'll get an answer, right? How did they do it in the book, I wonder? I think they did something more sophisticated. Yeah, they used a chain rule. I think that's what they did. D, dt. So what they did is they said this. How did they do? What are they doing exactly? So with respect to t, dx dt. Well, let me just do it the way it makes sense to me, right?
oh,
Right? So this is dy dx. And let me write down the chain rule again.
so they pretty much use like more likely a geometrical derivative. Because it seems like they to use like just leave the dt, they just put more. They split the dx dy.
So what I'm going to do, if I use it, I'm going to use a chain rule, but instead of y being y, is going to be dy dx. So let's apply the chain rule here. In other words, this is the derivative with respect to x of, not y, but dy dx. Right. I'll use a different color to make it clear how I'm doing the substitution. Right. So instead of using a y, I'm using dy dx. See that? That's the chain rule. But this is in this form, it looks more complicated, but it actually makes things easier. Because now I can see, right? So applying that here, dy dx, right? So dy dx is 1 over t, right? And dx dt is easy. So the derivative of this is difficult because this is a t, that's x, and sadly it's not a constant with respect to x. But in this form, now I'm taking the derivative of this with respect to t. And that will be business as usual. And that is the derivative of this with respect to t, which we saw as 2t. So you really got to pay attention to what you're taking the derivative with respect to. I'd really want to kind of shy away from using prime notation, especially now.
That's like when